All right, hello everybody. Welcome to the midterm review session for EE 105. The way this is going to go is we got a couple of questions, or I should say requests for certain topics to be covered. Actually, those people aren't even here yet. So I'm going to go through the exams right now, and then we can talk about other topics or anything that comes up in the meantime. Does anyone have any logistics questions or questions about the exam? Everyone can hear me okay, I'm assuming.
I was going to ask, will the full solutions to these two midterms be posted at some point before the exam or no?
I don't think so. Yeah, that's up to Professor Nguyen, and it sounds like he's not going to do that. So this is the means by which you'll get solutions is this review session, or if you want to come to office hours, we can kind of give you solutions. Okay.
I had a quick question about like the length of the exam. I think the professor was saying like since it's open book, it's gonna be longer than like the exams like that we got as practice. So like, do you know any information? Like, should we expect it to be a little bit longer than these exams?
Honestly, yeah, I'm not going to be able to add any insight beyond what he told you because I don't think it's quite finalized yet, first of all. And I definitely won't see the exam before you all do. That's just how it usually goes is I'll see it when you do. Yeah, it as far as length, it's also that it becomes kind of subjective to when you get more design type problems on the exam, which sounds like what he wants to do. So, maybe a little longer than these exams, but I would imagine not significantly longer. But again, I don't know. So whatever he told you is probably the best assumption to follow.
Yeah, thank you.
Yeah, no problem. Sorry, I can't give you more definite info. But let's get started here. So this is the 2018 exam. And so the first question is device physics, p-n junction. And so this should be pretty straightforward. Part C is a little different, but the first part, you're just asked to kind of draw the regions of fixed charge with the sign, and then the regions of mobile charge with the sign, or the type, or electrons or holes. And so there's no applied bias here. So what we're seeing is just the depletion with zero bias, right? And so the first thing to note when you're looking at a p-n junction is the concentrations on the p and the n side. Well, I guess the first thing to note is which side is p and which side is n. Okay, so phosphorus is n-type. Oh, of course, my pen decides to stop working. I'll just kind of talk through this while I'm changing my battery, but phosphorus is n-type, boron is p-type. And so that's the first step to this problem, is this is the n side, and this is the p side. Well, I'm not going to write there, actually. It's right here, n and p. And then the next thing to look at after you determine which is n and which is p is the concentrations, and mainly the relative concentration. So the n side has a lower concentration by about 1,000. And so when we draw the depletion region, that means that to get the same amount of charge on the n side, we will need a wider section of the depletion region because the concentration is lower. And so this should be review, but the n side, the depletion region, consists of dopants that have lost their electrons. And so they'll have net positive charge. And we usually draw fixed charge with circles around them. Same thing, kind of continuing throughout this region. And then on the p side, it's just the opposite is true, right? You have acceptors, they gained an electron. And so they were neutral to start, and then they become negatively charged once they gain an electron, or the more proper way to look at this is once they lose their holes. And so the mobile charge should be obvious at this point if you've already determined which side is p and which is n, right? You have holes here, the p side, and then you have electrons here in the n side, and those are the mobile charge carriers. And so, we have the condition here is that Q on the n side is equal to Q on the p side, where Q is the fixed charge. And so that Q, remember, is going to be something like the elementary charge constant times the cross-sectional area, which is going to be something like the width. Well, actually, I won't use W. I'll call this the thickness here. And this is the height. So this is the cross-sectional area times the depletion width, where this is WN and this is WP. All times the concentration. So if we're using Wn, that means we're looking at the concentration on the n side. And then we could write the equation for the p side, where it's QA times WP times the concentration on the p side. And so because our ND is lower than our NA by 1,000, that means Wn will be 1,000 times WP, which is approximately equal to total depletion width. So I've drawn, the depletion region as being almost evenly split between the two, but in reality, most of the times, if you have a difference in concentrations like this, the depletion region is almost entirely on one side. So in this case, it'd be almost entirely on the n side. Any questions about this? So part B is just asking which region of fixed charge is wider and why. And so I just went over the answer to that. The n side has a wider region of fixed charge or depletion region due to its lower concentration and the fact that the total charge in the two depletion regions are going to be equal. So the next part is suppose energy large enough to separate valence electrons from their atoms, e.g. from a laser, impinges the structure at a point just outside the fixed charge region on the right side. Describe how this induces current flow when a load connects across the left and right ends of the structure. Indicate the direction of positive current flow on the figure. And so if this is our p-n junction, and we have our depletion region there, what we're saying is that a laser hits the structure right here. And if it removes valence electrons from their atoms, that means it creates an electron hole pair, or I should say it creates electron hole pairs, right? So every electron that leaves its atom's valence shell leaves behind a hole in its place. And so that electron has an associated hole. And so before we think about the laser, right, we have our holes on this side, this is P, and we have our electrons on this side, so that's N. And then we get at this point, which is the interface between the quasi-neutral region, which is this region here on the P side, and the depletion region, we get new electrons and holes. So for every electron, we get a hole. And so you don't have to think about the two types of currents, right? We have drift current and diffusion current. And so first let's talk about diffusion. So if we get an influx of electrons and holes, that means our electron and our hole concentration is going to be higher at that point, which means that both electrons and holes are going to want to move out from that point in both directions to normalize or equilibrate the concentrations. And so what happens is we have this fixed charge which creates an electric field, right? We have an electric field that points this direction, right? And that's the direction a positive charge will move. And so any hole that by chance makes it over to the left side of this this region, or I should say over to the left side of this dotted line, so inside the depletion region, is going to get swept out by the electric field or pushed back out. And so really the holes cannot diffuse to the left because that electric field is like a potential barrier blocking them. So really the holes will just diffuse to the right. Electrons will diffuse to the right as well, but any electron that diffuses to the left will get swept across due to that electric field. And so what we end up with is our holes are mostly, almost entirely actually, diffusing to the right, and our electrons are going to mostly be drifting due to that electric field. And so what we'll get is basically two components of our current. And so let's draw the load here, just a resistive load. And so the whole current is going to be in this direction. So that's the whole diffusion current. And then the drift current of the electrons, well, the electrons are moving from right to left, which means the current will move from left to right. So the electron drift current is actually in the same direction. So these two components are going to add to give a total current I in this direction. So on the original figure, right? It's like the current is moving from left to right. And that's the answer to this problem. Any questions about this?
Yeah, I had one question about, I guess like the way I thought about this was like, since we have electrons on the positive side, like I thought, isn't it possible that the electrons would diffuse to the right because there's like a lower concentration of electrons at like the very right side of this like diode, I guess. Like I think in lecture, like I remember like whenever you have a bunch of electrons like built up near like the depletion region, they would diffuse to the right, but I'm not sure.
Yeah, so you would have electrons diffusing to the right, but the thing is you have so many holes on the p side that the electrons will actually recombine with those holes before they can actually create current. And so most of those electrons that stay on the p side, so the ones that don't get swept by the electric field, are going to just recombine because there's so many more holes in electrons.
Oh, I see. All right, that makes sense. Thank you.
Yeah, so that's why the electron current is really just the drift current. Okay.
Hi, Karen. I have a question. I'm not sure whether the laser will increase the depletion length or decrease the depletion length.
It's not really going to do either because it's just creating electron hole pairs. So, I mean, I guess if anything, it would decrease the depletion width, but it's going to be, I think, very minimal, and that's not really the main effect here. And the reason it would be decreasing the depletion width would be because you have the recombination of electrons and holes. But yeah, I don't think that's really going to be significant at all here. Because you're not going to be changing the concentration drastically. And so the depletion region is really formed by that, the two doping concentrations. And so you're not going to be changing that. And you're not adding more holes or more electrons. You're adding equal amounts of both, kind of. Okay. All right. I'm going to move on to the next part of this exam. And so for this problem, you know, it's a form of a non-inverting amplifier, but it looks a little different because we have this capacitor here. But and this is common for his exams, is he likes to give you something you haven't seen before. But the reason people, you know, make mistakes is oftentimes they think something is different in the scenario or something that we learned doesn't apply, and it's really the easiest kind of way to get tripped up. But just try and remember that the rules that we've been kind of repeating over and over throughout the semester are still applicable. You should just kind of adapt them to or not even adapt them, but use them in the circuit. And so the first question says, derive the transfer function as a function of the variables in circuit diagram. If applicable, your expression should be clearly, divided into a DC magnitude and a frequency shaping term. And the op amp is ideal is the most important part. And so if the op amp is ideal, that means that V plus is equal to V minus. Which means that this capacitor is essentially shorted out, right? You have no voltage across the capacitor. If you have no voltage across the capacitor, it's not doing anything. So now all of a sudden, we have the circuit we get for A just looks like this, where we have R1 and then our negative feedback. But that capacitor is no longer in play. And so this should be clear to you that this is just a unity gain buffer. That R1 is not going to do anything really because we have no current flowing into our input terminals because the op amp is ideal. And so V over VS, or sorry, V over VI just becomes 1. And so this is when the op amp is ideal. And there's no frequency shaping term, so you don't have to split it up. Okay, there's no S dependence. So it becomes a unity gain buffer. Now you're told to assume that the op amp has finite gain, but is otherwise ideal in all aspects. So no finite bandwidth, no input offset, no input bias current, right? Just finite gain. And that finite gain, remember, is what's going to make V plus no longer equal to V minus, because that assumes infinite gain. And so now that we have finite gain, we have to derive an expression for the transfer function as a function of that finite gain A naught and the variables given in the diagram. Again, splitting it up into our two terms. So for part B, what we get is, and there's two ways of doing this. So the first way, I'm going to do it just the typical kind of brute force circuit analysis. Our VI, our RI, and then R1 and C1. And VO. And so the first thing to do is to kind of write our expression for output as a function of input and the finite gain. So VO, we know, is going to be equal to that gain times V plus minus V minus. Well, V minus, excuse me, is equal to VO, right? And so we can rewrite that as A naught times V plus minus VO. And then we can write an expression for V plus as V naught, or V out over A naught plus V out. And so now we need an expression for V plus as a function of Vn. And we can get that by doing KCL at the non-inverting terminal. And so we get KCL at V minus, we get that VI minus, sorry, at V plus, that's what I'm doing KCL at V plus. So VI minus V plus over R1 is going to equal the current going through C1 because no current will go into the op amp, right? And so that current is equal to V plus minus VO over 1 over SC1. Okay. I'm running out of room here. So I'm going to continue this just in my notebook here. Okay, so that KCL again is VI minus, and then I'm going to substitute for V plus. Remember, I have V plus is equal to VO plus VO over A naught. So I'm going to substitute that in, because in the end I want only VO and VI. So this is V plus there, all over R1 is equal to, and then again, I have V plus on this side. So I'm going to substitute that for VO plus V over A naught. Again, this is V plus minus VO. And I'll just multiply that by SC1. Okay, so this is the same KCL equation. Now I basically get that VI is equal to VO times 1 plus 1 over A naught plus S R1 C1 over A naught. Now I just need to move that to the other side. And so V over VI is equal to 1 over all of that. And you're not done at this point, or we're not done, because we want to put this, split this into a frequency shaping and a DC magnitude. And so I guess the rule of thumb that I go for, right, is I look at the highest order term in my numerator and I match that to the highest, or I match that to the same order of term in the denominator. So I have basically a constant in the numerator, no S term. And so I want my constant in the denominator to be 1. And so actually first I'll multiply everything by A naught. So I get 1 plus A naught plus SR1 C1, right? And then now I'm going to pull out the numerator, I'm going to pull out A naught, and in the denominator, I'm going to pull out 1 plus A naught. So I get 1 in both my numerator and my denominator. And then my S term is R1 C1 over 1 plus A naught, because I pulled out that 1 plus A naught in the denominator. And now we have our DC gain, and then our frequency shaping term. And so the DC gain, the DC gain is given there, and then the pole frequency is going to be 1 over that, this is equal to 1 over that term multiplied by the S. So 1 plus A naught over R1 C1. And that's it for this problem. I want to quickly go over it another way, just because someone asked about finding feedback factor and things like that. And so this is the way that I would do it, especially on an exam, because the feedback factor method can be a little tricky, and I feel like it opens you up to more mistakes potentially. But if we look at the circuit again, then we can redraw this using the block diagram approach. And so if we do that, it's going to look like this, where we have our input, and because we have that R1, we have an alpha term. So even though this is a non-inverting amplifier, we have some basically change in voltage between VI and V plus. And so just generally speaking, I'll call that alpha of S, because we have that C1, we know that there might be a dependence on frequency. And then that goes into this summer where we have the output of the summer goes into our amplifier where it's A of S, I guess, but because we're considering finite bandwidth, or we're not considering finite bandwidth, excuse me, A of S is just A naught, right? And then we have to, of course, include our feedback factor, which is going to be, again, something that beta of S, because we have a reactive component, so we'll have something that's dependent on frequency. And because it's a negative feedback, right, we're gonna basically take that and subtract it from whatever's coming in through our input. Okay, any questions about this model that I've drawn? And so the part that's tricky here is that usually in our amplifiers, we have either the inverting or non-inverting terminal grounded. And so when we're thinking about the alpha and the beta terms, we need to think about how V out and VI feed back into the input in this behavioral model or this block diagram. And the input really is V plus minus V minus, right? Because the amplifier A of S is going to operate on V plus minus V minus. So input to the amplifier is kind of defined as that differential input voltage. And when V minus is, say, grounded, well, that just becomes V plus. But it's not grounded in this case. And so that's why I say this kind of opens you up to more errors. And so to get alpha, first off, we want to ground the output, break the loop, and then find that how the VI feeds into the input. So I have my VI, I have my R1, I have my C1, and then I guess I'll do it like he did it, where we kind of use dotted lines to show where the op amp was. But since we've broken the loop, we want to take the op amp kind of out of the equation so that we can just look at how this network of this RC network modifies V in. And so we're going to ground V out because we're looking at V in feeding forward. And so the circuit we end up with looks like this. And what we want to know, I guess the definition of alpha in this case is going to be V plus minus V minus, like I said, divided by VI. Because if we go back to this block diagram, we see that alpha is operating on VI and it's going to give us some input voltage. And so that's why I'm saying I want to figure out how VI is converted to V plus minus V minus in order to get alpha. Well, luckily V minus in this case is grounded, right? So I basically just have V plus over VI. Well, V plus I know in this case is just the voltage divider formed by C1 and R1. And so I'll use the impedance of C1, or I'll write this. So the impedance of C1 over the impedance of R1 plus the impedance of C1 times VI. All right, that's my V plus. And so what that ends up being is 1 over SC1 over R1 plus 1 over SC1 times VI. And so if I divide that by VI, I'll get my alpha, which means I get 1 over 1 plus S R1 C1. And that's my alpha. And again, this is already kind of taking more thought and time than I think the other method, but I just want to give you an example of how this works. And now, so this is alpha. And now let's find beta. And it's kind of the inverse, right? We're now going to ground the input and figure out how V out, I should say we're going to ground VI and figure out how V out feeds back to our amplifier input, right? And so to do that, we're going to take our input, or our VI, and ground it. We have our R1. Again, we have to break the loop. Then we have our C1 here. This is where the op amp was. And then we leave our VO here because we want to figure out how VO feeds back to our amplifier input. And again, I'm going to write a definition for beta, where beta is going to be the input to the amplifier in our block diagram, which is V plus minus V minus, over VO. And so this time around, we don't necessarily have either V plus or V minus grounded, but we have V minus is VO. Right, so this is our beta. And so did I get this right? Yeah, so again, we can write V plus as a voltage division of VO. This time with R1 in the numerator over R1 plus 1 over SC1. And so if we want to get beta of S, now we can take that term divided by VO, which just ends up being S R1 C1 over 1 plus S R1 C1. So I just multiply the top and bottom by SC. And then I divide by VO, right? Because I have this VO in the denominator, and then minus 1. So I can say that's S R1 C1 minus 1 plus S R1 C1 all over 1 plus S R1 C1. I might have made a slight error here. Let me double check. So, yes. So beta of S is going to basically be subtracted from our input, right? When we look at our block diagram, beta of S is negative feedback. And so really what I should have written here is that beta of S is equal to V minus V plus, right? That's the negative of the input to my amplifier is V minus V plus. So this becomes VO minus V plus. This becomes 1 minus that. And so we get basically flipping the signs, we get the same expression actually. 1 over 1 plus S R1 C1 is beta of S. Right. And that's because beta has negative feedback. And so that's why I kind of defined beta as the ratio of the negative input to my amplifier divided by V out. And so this is kind of a coincidence that this alpha and beta are the same. It's not something you should ever assume. And so at this point, let's go back and let's write the expression for our gain based on that behavioral or the block diagram. So you'll recall, or go back to the lecture notes, that if we analyze this block diagram, we get that VO over VI is just alpha of S times A of S over 1 plus beta of S times A of S. So this is kind of like the A over 1 plus beta times A, but we have the alpha term as well. And at this point, I think I'll leave this exercise to you, where we have 1 over 1 plus S R1 C1 times A of S is just A naught, remember that, because we don't have finite bandwidth in this case. 1 plus beta times A of S. That's beta again is 1 over 1 plus SRC1. So we get A naught over 1 plus SR1 C1. And if you rearrange this, you will get the same transfer function we got here. So I just wanted to give another approach to this problem. I wouldn't use this approach myself on an exam, but you know, hopefully this gives you some more insight into how these problems work. Okay, any questions about that? So we got our transfer function, and now we're told to assume the op amp has finite gain and draw the magnitude Bode plot for the amplifier circuit on the given graph using the following values. And you're kind of told, and this is, if you have a problem like this, you'll probably have the same stipulation that if you didn't get an answer, you can make up a transfer function, or just, if you're not sure, you can plot the transfer function for what you got. This part C is looking at, can you draw a Bode plot given a transfer function? And so basically we're just going to plug in the values. So our DC gain, if you remember, it's just A naught over A naught plus 1. And then our pole frequency, right, is just going to be 1 plus A naught over R1 C1. So you basically have everything you need to calculate the values for this DC gain and pole frequency. And what you should get is that the DC gain is very close to 1, right? Because A naught is large, and so A naught over A naught plus 1 is about 1. And then the pole frequency is going to end up being 10 to the 7 radians per second. And so for part C here, I'm just going to draw a single time constant low pass response with a gain of 1 at DC and a pole at 10 to the 7 radians per second. Or go down 20 dB per decade. So this is C. Now D says, assume that the op amp not only has finite gain, but also finite bandwidth. And you're given that bandwidth, it's 10 radians per second. Plot the magnitude Bode plot for the op amp only. So open loop response now is what we're being asked for, labeling it D. And so now for D, our gain was 10,000, so that's 80 dB. And our bandwidth is 10 radians per second. And so what we get is something like this. Again, single time constant, where we have, this is part D. That's our open loop gain, A naught, and that's omega B. Pretty straightforward so far, but please stop me if you have any questions.
So for this case, the gain bandwidth is not the same in these two situations, right?
Well, no, because in the first case there is no bandwidth. There's no bandwidth to the amplifier in part C. We're assuming it's infinite bandwidth. Yeah, that's correct. And so that was D. Now E says, assuming that you basically are using this amplifier we gave you in D with the finite gain and the finite bandwidth. Now use that in your circuit and draw the closed loop gain frequency response. Use the dotted line, okay, yeah, to distinguish it from the others. I'll use purple. And so this is really a graphical kind of solution where I'm not even going to, if I tried to plug in, so to be clear, right, part D says that A of S is equal to A naught over 1 plus S over omega B, right? That's the expression for a finite gain bandwidth open loop response of an amplifier. If I try to plug this back into my original transfer function, I'm going to get a two-pole transfer function. So S squared, it's going to be messy. It's going to you're going to use up your exam time doing algebra. And so what you should do is realize that you can just graphically solve this, because we have basically now a non-inverting amplifier that's going to, as long as the response is less than the open loop response, it's going to do its original thing, which is have a gain of 1. And then what's going to happen is as soon as we hit the open loop response, we're going to track that. And so what we get is basically the combination of the open loop and the closed loop response. And yes, there will be another pole out here, right, or something where I'll go down again. But that's off the graph. I don't care about it for this problem. And so part E is really just completely graphical. All right. Okay, that's all of the kind of gain bandwidth stuff. And then the next part here, so any questions about A through E?
I have a question about E.
Sure.
I'm not sure whether, can you go to the previous page about the dot line and the red line? I think, I don't know whether that 10 to the power of 5 is the 3 dB point.
Yes. Yeah, so if we zoomed in here, maybe I'll draw it up here. So you're asking, is 10 to the 5th radians per second our 3 dB frequency for the closed loop response?
Yes.
Yeah, it is. So this is not very neat, but you know, imagine this is 10 to the 5th. Then our open loop response, you know, is going to be exactly equal to 1 at that point. But the closed loop response, right, the asymptote will hit that point, but in reality, the actual curve will start dropping before that point. And so here, this is 1 over root 2, or negative 3 dB.
At this point, it should be A0 multiples omega B. So it should be, if we just solve for the double pole equation, we might find this actually is the square root of 3 instead of square root of 2.
I'm not quite sure what you're asking.
I mean, if we just plug in everything and solve for the equation, and I take in that point about 10 to the power of 5, the frequency of 10 to the power of 5, the turning point I got, it's like, it's 1 over square root 3. It's not 1 over square root 2.
Yeah, it's probably because there's a second pole, right? So the second pole, if it's not far enough away, it could cause the slope to be slightly steeper. Yeah, I'm not sure because I can't see your work right now, but generally speaking, that's not a concern because what we're doing is we're treating this, we're only looking at kind of the dominant pole here. And plus there's nothing in the problem that asks about what the exact magnitude is at that point. And so it's going to be roughly equal to negative 3 dB. Honestly, my instinct is that it would be equal to negative 3 dB, but it's possible that the proximity of the poles means that it's not a perfectly single pole or single time constant system. That's why we can't make that approximation. But again, that doesn't really make a difference in this problem.
Kieran?
Yeah.
I'm a little confused about the connection between like D and E with the earlier parts of this problem. So I just don't get what E's saying. So now use this op amp for the above circuit. If this was like, I thought we were analyzing this same op amp, but then in part D, we were just doing open loop. Then how, I don't really understand, like, how is there this new Bode plot now? Like this new omega B and whatnot for that same circuit. Like, I'm confused. Did we like swap out this op amp with a different op amp? I don't quite get it.
Yeah, so we initially took, so I guess If the op amp, let's just say it has a frequency response we'll call A of S.
Sure.
So for A, A and B, I think. No, just for A actually. A of S is infinite. And then for B, we now say A of S is A naught. Same with C. So I guess B and C. And then D now, we say that A of S has that finite bandwidth or finite gain, but it also has finite bandwidth. So it looks like a single time constant low pass with DC gain A naught and a pole frequency of omega B.
When we read the words finite bandwidth, that just means basically this equation you have just written.
Yes, yeah.
Okay.
Or if you see omega B given.
So this is
Or-
essentially like literally it literally is a different op amp then.
Yeah, but it's not, I mean, a good way to think of it too is that, maybe I have it's a different op amp, but we're kind of taking approximations and then approaching now the real op amp. So in the beginning, we made a bunch of approximations, and then by part D now we're looking at a more realistic model for an op amp, which is kind of how we do a lot of these problems, right? Is we look at the ideal case to get some intuition about what's going on, and that ideal case kind of is how we realize this is going to act like something like a unity gain buffer, and then we now take the finite gain into account, and that tells us, okay, well, now that C1 is going to give us a pole in part C, we have that pole. And then we take it a step further and say, well, not only does C1 give us a pole, but we're going to assume that there's an internal pole in the op amp, so the finite bandwidth of the open loop response. And then that's how we get the green curve.
I guess to clarify my question a little bit, and it's pretty quick. Like for part E, if we're using the same exact circuit as before, then our omega B would still just be 1 plus A naught over R1 C1, right? And they literally say that we're using the same A naught as in part C.
Well, no, omega B is not omega. So omega B refers to an open loop pole.
Oh, okay, so this was just a general pole frequency given that circuit. So omega P is not the same as omega B.
Right. Omega P is a general pole, and it'll depend on your circuit. But omega B is more a property of the op amp.
Okay,
So,
and it's just going to happen regardless of the circuit elements that are around.
Yeah.
All that matters is the gain.
That
Or the
was
DC
10
gain.
in this case, right?
Sorry?
That was 10 in this case, right? That was given?
10 radians per second.
Okay, so then in
That's
that case, since we're given omega B, all we care about is the gain given the new circuit elements, which created this gain of 1. That's what we
Sort of. I mean, graphically though, omega B here sets that effective 3 dB frequency now that we put it in
right.
Yeah, in feedback.
I'm just saying we use the circuit elements given that we're using this op amp. The only thing we can use the circuit elements for is to find that gain, since we're kind of not using it to solve for omega like a pole anymore.
Yeah. We're basically we're taking the gain that response we already solved for, and we're graphically seeing that pole that was in the original solution when we assumed infinite bandwidth of the op amp, that's going to be further out than the pole that we get from that op amp finite bandwidth, and so that the lower pole is now like the dominant pole.
Okay, thank you.
Yeah, and yeah, no problem.
In this case, should D and E obey should D and E have the same gain bandwidth product, or is that just a coincidence?
Yeah, they should. There might be a slight. I'm not actually 100% sure if the curve will be slightly less or below the open loop curve because of the presence of that alpha term, but to first order approximation, just assume they have the same gain with bandwidth product. Yeah. And that kind of only applies until you get to the second pole, right? Because once you hit a second pole, or once you see the effects of a second pole, so once your slope increases past 20 dB per decade, the gain bandwidth product is no longer constant. Okay. What other questions do you have? I'm happy to help answer.
I had a question. So like I was trying to solve for the 3 dB frequency for part E, but it seems like it's just super, super complicated. So like, would you say that it's even worth it to try to calculate the 3 dB frequency on an exam, or like we should be pretty safe with just doing like this kind of graphical solution?
You should be safe. I mean, think about what we've seen in so far in this class. I don't think we've given you any problems that are two-pole systems where you have to calculate the 3 dB frequency, really. Right. And just in general, that kind of very rigorous like derivation is not something I think Professor Nguyen wants to test you on.
Okay, cool. Thanks.
Yeah. Generally speaking, if you find yourself doing a bunch of algebra, you might want to go back and think about if there's a simpler way to do the problem. Generally speaking. Let's move on, if that's okay. So the next part, you're basically told, now forget everything from the beginning. We're going to use the op amp in part D, and it's going to be basically a non-inverting amplifier with a closed loop gain of 100. And then you're told the slew rate and the input signal, and you have to determine if the output is going to cause slewing. Right. And so I don't really have room here, so I'm going to move to my notebook. So the first thing to note is that your unity gain bandwidth, right, is going to be A naught times omega B. It's 10 to the 5th radians per second. And so we can now use this to find the gain bandwidth product, or I should say the bandwidth for a given closed loop gain. So our closed loop gain is now 100, and I'll call this omega P. It's just the bandwidth of my closed loop amplifier. And so omega P is going to be equal to 1,000 radians per second, because this is 100 volts per volt given in the problem. And so this is an important thing to think about. Anytime you're given a new closed loop configuration, we're not worrying about what the component values or anything like that right now. We're just told the closed loop configuration is 100 volts per volt. And so we're going to assume the same gain bandwidth product and figure out what the new closed loop bandwidth is. And why is that important? Well, if our frequency is above that, then we know we're going to get attenuation, right? And so now we can write a general transfer function based off of what we're told. We're told the gain is 100, and we're going to assume it's a single pole system, because really, once we get to that, I should say at the frequency we're talking about, we're not going to be concerned with a second pole or anything. And so, again, I'm using the basic form of a single time constant low pass response with my DC gain of 100 and my omega P of 1,000. And so now what we need to do is figure out what the effective gain is at the frequency of our input signal. And so to do that, we take the magnitude. So we want the magnitude h of j times 10 to the 5th, because we're given our input signal is 10 to the 5th. Or sorry, it's 2 pi 10 to the 5th. So it's 100 kilohertz, which is 2 pi times 10 to the 5th radians per second. So we want to figure out at that frequency, what is the magnitude of our gain? And so the numerator, it's just going to be 100, and the denominator is going to be 1 plus 2 pi 10 to the 5th over 10 to the 3rd squared. So I'm just basically saying this is 100 over 1 plus j times omega over 10 to the 3rd. Right, and to take the magnitude, I just take the imaginary component and the real component, I square them both, add them and take the square root. So the magnitude of the gain becomes 0.16. So we don't have much gain at this point. And then, you know, at this point, you know, you should start to think, okay, maybe I'm not going to be slewing because my output is actually going to be smaller than my input, but I need to figure it out. And so the output signal, so I should say the input signal is, we're told 0.1 volts times sine of 2 pi times 10 to the 5th t. And so the output signal is going to be equal to 0.16 times 0.1 volts times sine of 2 pi to the 5th t. Right? It's going to also be sinusoidal with the same frequency. We're not getting a frequency shift or sorry, phase shift or anything like that. And so now we need to figure out dV dt max. Well, that's just going to be equal to the amplitude of the output times frequency. And so that's equal to 0.016 times 2 pi 10 to the 5th. And that's equal to 1.005 times 10 to the 4th, which is less than our slew rate given as 1 volt per microsecond, which is the same as 10 to the 6th. So no slewing will occur. And so with this problem, you know, it's important to figure out what the new transfer function looks like, figure out what the gain is at the frequency of interest, which is 2 pi times 10 to the 5th. And then from that, figure out what your output signal looks like in terms of amplitude and frequency. And from that, you can figure out what the max dV/dt of the output is.
Kieran, how did you know that there's no phase shift in this case?
Because basically before that capacitor comes into play, it looks like an open circuit. So before that, we hit the second pole, essentially, it becomes an open circuit. The caveat is even if there's a phase shift, that's not going to change the max dV/dt.
Okay. Mm-hmm.
But if you're curious, yeah, if we're basically assuming that we're low enough frequency that we haven't hit that second pole yet, that capacitor is still kind of like an open circuit because its impedance is still large. And so at that point, we just have, you know, a non-inverting amplifier, or unity gain buffer, basically. Well, sorry, not unity gain anymore. Actually, you know what? Scratch what I just said. There's no capacitor even implied in this part of the problem because you're told that the op amp of part D, so an op amp with finite gain of 10,000 and finite bandwidth of 10 radians per second, is used in a non-inverting amplifier with a closed gain of 100. So really, you know, if you wanted to think about it, you could say, okay, I have, I have this circuit. Where, you know, it's roughly something like this. That's going to have a gain of 101, but you get the picture, the idea. Mm-hmm. And so, yeah, non-inverting amplifier, no reason there would be a phase shift. Okay, any other questions about this problem, or should we move on? Okay, so that's the end of this exam. Oh, sorry, that's not the end of this exam. Is it? No. Okay, this problem is deceptively simple. And so, again, this is the case where seeing a MOSFET with an op amp, you know, might just stress you out. It would stress me out if I saw this on an exam. But, you know, always come back to your fundamental op amp laws and your MOSFET IDS equation, and you will be able to figure this out. And And so again, you're always looking for the simple things that you can kind of determine quick first to get some footholds in terms of, you know, solving for things in the problem. And so the first thing you're told is, you know, assuming an ideal op amp, calculate the DC voltage at VO. Well, if we have an ideal op amp, that means that VI at the non-inverting terminal is going to cause the inverting terminal to be VI. If I know VI and I know the other side of RS is ground, then I can get this current, which in the case of part A is ID, right? Because I have no current flowing into my op amp. And so this is just ID going through RS. And so for A, I can say that ID is equal to VI minus 0 over RS. And I just get that ID is going to be 250 microamps, I believe. 0.25, yeah. Why do I care about ID? Well, if I know ID, I know the current through RD, because there's no current here, right? The current through the gate of a MOSFET is also 0. And so all that current will flow through RD. Well, if I know ID and I know RD and I know VDD, I can very easily get VO. My erasing is very finicky. VO is VDD minus ID RD. We know ID, we know RD, we know VDD. We get VO is 1.5 volts. So that's the first part right there. I didn't even have to pull out my MOSFET ID equations. I'm just using the ideal op amp laws and then Ohm's law.
How do we know that? Is it true that for MOSFET the current into the gate is always 0?
Always 0.
Okay, so regardless of whether it's operating in the linear or saturation region, it's always 0.
Yes.
Okay.
A DC.
Okay.
So for part B, now we have to assume input bias currents of 100 microamps going to each of the input terminals, but otherwise ideal in all aspects. So now I have some I bias here and here. But I'm told that the op amp is still ideal in all other aspects. And so the first thing I can note is that, and now we're basically asked to find VA. And so to find VA, I need VI plus VGS here. And so yeah, the first thing to note is that VI is still present on the inverting terminal because we still are assuming infinite gain. Infinite gain is what means V plus is equal to V minus. And so since we haven't changed that assumption, V plus is still equal to VI, V minus is still equal to VI. So VI now shows up across RS, but now this current here is not 0, it's I bias. Because the current here is 0 going into the inverting terminal, but we have I bias now, which means that the current through RS is ID minus I bias, and the current through RD is still ID. Okay. And so again, to get VA, we need to find VGS. because we know that the inverting terminal is VI, and if we go up by VGS, we'll get VA. And so I'm not thinking about the op-amp's output generated by the op-amp. I'm thinking now about the MOSFET. And so if I want to get VGS, I need to figure out what IDS is, right? And so again, I can write a KVL, or actually, yeah, I can write a KCL at that VI node, or I can say that I bias plus VI over RS is equal to ID. And I'm assuming saturation, and most of the time, I can't think of a case where I wouldn't assume saturation unless I saw something that looked exactly like, lab 3 or something like that. But I'm always going to assume saturation to start, and then I'll go back and check that assumption once I get my operating point. And so the other thing to know is this is all DC. We're not really thinking about anything AC right now. And so ID, we know, is equal to, in saturation, mu n Cox over 2 times W over L times VGS minus VTN squared times 1 plus lambda VDS. So that's my saturation current equation. Well, now I could write VGS as a function of ID, and I get that VTN plus square root of 2 IDS over mu n Cox W over L times 1 over 1 plus lambda VDS. So I just rearranged my ID equation to get an equation for VGS, because again, that's, if I know VGS, I know VA. Well, one thing to note is that my body bulk terminal here, now we told, yeah, bulk tied to ground. So up here, the bulk is tied to ground. And so that's important for my effective threshold voltage, right? We know that if I have a non-zero VSB, I'm going to have a change in my threshold voltage, and VS is VI, right? And so VSB really is going to be equal to VI. So this is my equation for VGS. And now we kind of have two equations, right? One for this equation here, this equation here. And our unknowns are IDS and VGS, because we know VI, we know IB. And so first we can solve for ID from this equation, because we know VI, and we know RS, and we know IB. And we get ID is 350 microamps. Well, now I know ID. I need to find VTN, and then I can find VGS. And so VTN is just going to be equal to my VT0 plus gamma times this whole expression, square root 2 phi f minus VSB minus square root of 2 phi f. Where VSB is just going to be VS minus VB is equal to VI. So I get that, actually it's plus VSB in this equation. And so I get that VTN now is going to be equal to, instead of 0.7 volts, it's going to be equal to 0.94 volts. And so now I have everything I need to solve for VGS if I plug in numbers, which you're welcome to do on your own time, you should get VGS as 1.13 volts. Remember, we need to check for saturation. Well, VOV is going to be 1.13 minus 0.94, 0.18 volts. That's less. And then we need to solve for VDS. VDS then, I'm running out of room, is going to be equal to VD, which is VDD, minus ID, RD, minus VS, which is VI. We know VDD, we know ID, we know RD. We can solve for VDS. And what we get is that VDS is 0.3 volts. And so going back to my VOV, that's less than VDS. So I know I'm in saturation. The last thing to do, I'm just going to write it up here, is VA, again, is going to be VI plus VGS. Since VGS is 1.13, VI is 1, I get 2.13 for VA. So again, this problem is tricky, but in reality, the mechanics of solving are not anything radically new. So, you know, keep in mind that if I know ID and I know my VT, you know, if I know all of my transistor parameters and I know ID, I could find VGS and vice versa. Yeah, I guess you would need VDS. You would have needed to solve for VDS before you solve for VGS. So you could plug it in here, but it's easy enough to do because it doesn't require you to know anything besides ID, RD, and VDD. All right, any other questions about this exam?
There's a question in the chat.
Oh, thanks. For transistors, both MOS and BJT, do we always assume saturation for calculations? Well, saturation means different things for MOS and BJT, first of all. So I would say you should usually assume saturation for MOS and forward active for your BJT, especially if it's in an amplifier of any sort. But yeah, forward active is the desired region of operation for most analog amplifiers. For BJTs, saturation is the desired region of operation for MOS. Okay, I want to go over the other exam, but I also do want to cover the requests I got on Piazza. So I guess the first thing I'll do is just talk about, maybe I'll just talk about the a diode problem like from homework, because I think we got had someone who wanted to get some more insight on how to solve the diode questions. And let me pull this up for you. Okay. So here's a diode problem from homework 5. The request on Piazza was, you know, how do we gain intuition about which diodes are on and off? And honestly, the answer is that you can make a guess, but you're always going to want to check that anyways. And so especially on an exam, well, I won't say especially, but on an exam, you know, you might want to just go through your systematic approach of assuming they're both on first. Because you're not going to waste time thinking about what's on and what's off. In the end, the way to determine what's on and what's off is really still doing an analysis. You could do an analysis without writing equations. So I think that's how I talked about this problem before. And so you usually, for a diode, you know, problem like this, you'll have two cycles where VI is positive and VI is negative. And so for VI positive, I would basically think about the currents. So if VI is positive, well, this is virtual ground, 'cause I'm assuming this op amp is ideal. That means my current's going to flow this way, my input current. If I have current flowing in that way, I know no current's going to flow into my inverting terminal. So all that current will flow up in this direction. So right off the bat, that I can see a possibility for current flowing through D1 in the forward bias condition. Let's think about the current flowing through R2. Well, if current flows through R2, in this case, we don't have any load resistor. But if current flows through R2, that means the only place for it to flow is back through D2. So in this case where I have VI positive, I have current flowing into this KCL node here. The current flowing out of the KCL node would have to be, would basically imply that D2 was off and D1 is on. I guess I could assume that, yeah, there's lots of assumptions you can make in games you can play in terms of like different cases or different directions of currents, but in the end, doing an analysis is the best way to verify. And so that would tell me that I think D1 is on, D2 is off. That's what ends up happening. I guess in the case that D2 is on, I would have current flowing this way, which means that VO would have to be greater than 0 because I have 0 here, current flowing through R2, which means VO has to be positive. If VO is positive, and I'm assuming, maybe this is your answer, is the best way to get intuition is to assume ideal diodes first off. The problem is the difference between an ideal diode and a constant voltage drop diode, it might be that the diodes are not actually in the same on state when you change that assumption, but most of the time, assuming an ideal diode is going to give you the same on state or off state as when you assume a constant voltage drop for the diode model. And so if I assume an ideal diode to get the intuition, well, that means that there's no voltage drop, which means that VA has to be ground as well, because D1 is connecting this virtual ground to VA. And so if VA is ground, then that means I would have, and VO is positive with the current directions I've drawn. Again, that implies D2 is off because I have a negative voltage, a reverse bias voltage. So that's kind of two ways you can attack that. And then let's talk about the case where VI is negative. Well, that means I have current flowing this way. If I have current flowing that way, again, I can assume initially that current is flowing in the same direction from both of these branches, which just tells me D1 is off. If I assume maybe current's going to flow that direction for some reason, well, okay, so I assumed current was flowing back through R2, which again implies that VO is positive. If VO is positive and D1 is on, again, that means VA is 0 volts and current would be flowing back through D2. So that kind of tells me that I can't have both D1 and D2 on in this case. And the other, approach I just took where I said maybe the current's going to flow back through D1, implying it's off, tells me that D1 is probably off. But again, all of these kind of tricks I'm talking about are ways of thinking about this almost qualitatively. I wouldn't necessarily recommend them because it's easy to get confused. And so just actually picking an assumption and solving will tell you a lot about, will tell you what you need to know. And so if I assume they're both on, the diode that gives me the contradiction probably is not on. Likewise, if I assume they're both off, the diode that gives me the contradiction is probably not off. Yeah, I wasn't sure how much to add to this other than what we've talked about. So I welcome questions about this. Okay. The other request I got was for rederiving small signal parameters and things like that. So I'm going to kind of do that quickly, but I'm also going to tell you that I'm really just going back to Professor Nguyen's lectures. And so they're a really great resource. And so I think there are times when they're not, reading back through them can be confusing maybe. So hopefully I can add some insight, but otherwise just looking at his notes is a good place to start. And so for small signal models, they're both the BJT and the MOSFET use basically the Y parameter model. And after we introduce this and derive the small signal models, we don't really go back to this generic Y parameter model often, but I'm trying to kind of rederive stuff so people have understanding, and that's why I'm going back here, but it's not something like I would ever really write on an exam probably. So the Y parameter model basically models a 2-port device where each port kind of has 2 terminals. And usually one of those terminals is ground, which is why we kind of think of it as just an input and an output, even though technically it's kind of 4 terminals. And so what the Y parameter model does is it takes the voltage and the current at each port and it relates them. And it also relates the current at one port to the voltage at the other port and vice versa. So basically it's a behavioral sort of model that describes the relationship between all the voltages and all the currents in this device. And so we have our V1, so this is port 1 and port 2. We have our V2. The Y values in this model, they're admittances. So when I draw resistors, I'll draw, the values of them will be 1 over Y. Y11 implies the current relationship I1 relative to the current at port 1 and the voltage at port 1. So 1,1 relates I1 and V1. Conversely, Y22 relates I2 and V2. And then the kind of trans conductances, Y12 relates I1 to V2. So we get, a current I1 that will depend on V2. Similarly, Y21 relates I2 to the voltage on port 1, V1. And so starting with this general model, we can get either the BJT, or the MOSFET small signal model. And so I guess an important thing is the definitions here. Y11 is defined as the ratio of I1 to V1 when V2 is equal to 0. So if we short, these 2 terminals on port 2, we're basically shorting out that Y22, and we get V2 is equal to 0, and so this goes away, the current source, because V2 is 0, right? And so at that point, I1 is solely dependent on V1 and Y11. Y12 is the current I1 is a function of V2 when V1 is equal to 0. So again, if V1 is equal to 0, then I'm shorting out that Y11 resistor. That's not going to affect my current. All I have is the current source here, which says that I'm going to have a current dependent on the voltage at port 2. The others are similar. Y22 is relating the current at port 2 to the voltage at port 2 when the voltage at port 1 is 0. And then Y21 relates the current at port 2 to the voltage at port 1 when the voltage at port 2 is 0. So those are the definitions. And so basically when we're coming up with small signal models for, let's start with bipolar, the bipolar case, we should think about how the behavior of this device can be mapped to this model. And so we basically have that the total current is going to be IS times E to the total base voltage for VT, all times, what is it? 1 plus total collector emitter voltage over VA. So that's our derived current through a BJT. And so if we think about it, right, we have kind of three terminals here. And so when we draw the small signal model, we're going to basically, I guess I'll draw a more general case and then I'll show you how it reduces. So this is going to be the base, this is going to be the emitter. And this is going to be a resistance that describes IB, I should say it describes VBE over IB, right? Because this resistance is kind of like 1 over Y11, where Y11 is I1 over V1. So now we have VBE over IB. Hopefully that it's clear to you how that tracks. Y12, so let's draw the other side first before we draw the current sources. So the other side, we're going to look at how the collector and the emitter are related. So the collector is going to have some input current IC, and we're going to call this resistor R0. And this R0 is like 1 over Y22, right? It's going to relate the voltage VCE to the current IC. Now, do we have a basically a mechanism for VCE to change IB? Not really. And if we look at our equation here for our collector current, VCE is not going to change IB, it's going to change IC. And so the Y12 source, basically VCE's effect on IB can be neglected. So I'll just draw it and then say we're not going to use it because it's not going to change IB. But we know that VBE is definitely going to have a strong effect on IC. And so we'll call that effect GM, all right here, GM, which is our, again, our transconductance. And that GM is just Y21. Right, so V1 becomes VBE, I1 becomes IB, V2 becomes VCE, I2 becomes IC, and then 1 over Y11 becomes R pi, 1 over Y22 becomes R naught, and then Y21 becomes GM. Well, now I can see that I have, the emitter here and the emitter here. I can basically connect those two parts of my circuit. And that's where I get the hybrid pi model that looks like this, where I have the emitter And then I have my GM source and my R naught here. So hopefully this maybe give you another way to look at where this comes from. So let's derive these parameters. I'm going to go through this pretty quickly because it's in your notes, and I want to go over the second exam. And so really the Taylor expansion is one way of looking at it. I'm not going to do that way because it's in your notes. Another way to look at it is taking the derivative of the total current with respect to certain things. And so R pi, remember, is 1 over y11. So it's going to be something like V1 over I1. And we're looking at small signal. So we're actually looking at VBE over IB, right? Actually, I'm going to start with GM. So GM is Y21, which again is I2 over V1. Well, we said I2 is IC, V1 is VBE. So small IC over small VBE is going to be equal to the derivative of the total current IC with respect to the total base emitter voltage at our operating point. And so to do that, you can basically take the partial derivative of IC, which from this R expression up here is just IS times the exponential here with our output resistance model there. And again, this is at the DC operating point. Well, if we take the derivative with respect to VBE, we just get IS times the same exponential. And I'm actually going to plug in my DC values for VBE, and then the whole thing divided by VT. So this entire expression there, well, that's just the DC value of our collector current. So that's why our GM is just the DC collector current divided by VT. Going back to R pi, well, if I have little VBE over little IB, I can also write that as little VBE over little IC over beta, right? Because we know beta relates IC and IB. Well, I see right here, IC over VBE is equal to GM. I have beta, 1 over beta in my denominator, so that goes to the numerator. And then I have IC over VBE. I'll write that in my denominator. So I get beta over GM. I could also have written this. I could have taken the derivative with respect to VBE of IB, taking the inverse of it, because it's a resistance, not a conductance in this case. And so if I did that, I would take my expression for IC and divide it by beta. So I take my IC expression and divide by beta. So I get IS over beta times everything else is the same. And this is at the Q point again. Then I take the inverse to get R pi. Well, if I take this derivative, I get something very similar, right? Where I get 1 over VT times IS over beta times the exponential, where I'll plug in my DC value because I'm at the operating point. in this entire thing is the DC value of IB. So I get IB over VT. Well, IB is just going to be IC over beta. Oh, yeah, sorry. Then 1 over this. So I get VT, and then I get IC over beta. Well, I get beta over IC over VT. We already know IC over VT is GM, so I get the same answer, beta over GM. So that's where R pi and GM come from. R naught is the same thing, except instead of taking the derivative with respect to VBE, I'm going to take the derivative with respect to VCE. And what I'll get is basically the same thing. This is in your notes too, but so it's the derivative of the total current IC with respect to now VCE, because again, R naught is like 1 over Y22, which if we remember, Y22 was I2 over V2, where IC is I2, and VCE is V2. So again, I need to take 1 over this for the resistance. It's at the Q point. And what I get is VA over IC. Went through that kind of quickly, but hopefully that gave you a little refresher. MOSFETs, it's similar. It's actually, mechanically it's the same procedure where I take the derivative of, but I just need to make sure I know what my terminals and basically my voltage, my V1, my I1, my V2, and my I2 are. And so drawing the small signal model for a MOSFET, I have my ID here, I have my VGS, and I have my VDS. Those are really the relevant voltages. And so I'm going to do the same thing where my S is going to be on the bottom. Well, I just told you that the current going to a MOSFET is always 0, which means you have infinite input resistance. And so if I look at that component, Y1 over Y11 here, that's defined as I1 over V1. Well, if I1 is always 0, then that's always 0, and 1 over 0 is infinite. And so I have basically a resistor with value infinity, replacing the 1 over Y11. This is my source, this is my gate, and then my Y21 is again going to be my GM times my V1, which in this case is VGS. My V2 now becomes VDS. And so my 1 over Y22 now is R naught. Same concept, right? Where it's going to be equal to the current ID. I should say it's going to be equal to the voltage VDS divided by the current ID. I guess I'll just say this IG is 0. And so this model is really actually the same as the BJT case, but beta is infinite. But doing the derivation, GM is basically going to be defined as the change in I2, which is the total current ID, with respect to the change in V1, which is total voltage VGS. And so if I take the derivative, the partial derivative, VGS, of my current equation in saturation, then I just get that my GM is equal to Kn times, I should say this is at the Q point still. So I plug in my DC values for VGS. And that's why I say it's Kn VOV. And we can also write that as 2 times ID over VOV. So again, same thing. I'm taking the derivative of the total drain current with respect to the total gate to source voltage, and then I'm plugging in my DC values for VGS, or in this case, for the other expression, for ID. I think I'm going to move over to the other exam unless there are more questions about these small signal models. But this is a great time to ask questions if there's things that are unclear about what I did or. Yeah.
Just like one small question about that
Mhm.
very last simplification you did to get 2 ID over VOV. Is that
Mhm.
assuming that lambda is 0?
Is that assuming lambda is 0? I guess it is. Yeah.
Okay.
But you can assume that you know, when you're most of the time, and even if you're not assuming lambda is 0, it shouldn't change things much. But yeah, well, actually, no, this is still going to be, yeah, this is technically, it's not assuming lambda is 0. Technically, this is still 1 plus lambda VDS, right? Because when I take the derivative, that 1 plus lambda VDS is still going to be there.
Right. Mm-hmm.
And so, yeah, I'm actually not making any assumptions about lambda. But, you know, for the most part, lambda is not going to affect GM appreciably. Okay. Gonna kind of go quickly through this midterm 2 or the fall 2019 midterm.
Oh, Kieran.
Yeah.
Oh, sorry. I had a quick question. Like, I think problem 1 of this exam was kind of like the one that we just did. So I was really stuck. I don't know about other people, but I was really stuck on the second problem because I had like no idea how to approach it. So is there any chance we could do it first?
Yeah, I'm totally cool with that. I think I can kind of give you, this is a really hard problem too. So I can kind of give you a start, and even if we don't get through it all, hopefully you'll, you know, have a better idea of what to do. Mm-hmm. So this problem is weird. Basically what we have is this sandwich of N and P type material. The doping is much higher here. Change colors. Is much higher at the edges. And so you should recognize that and then kind of assume that those are going to be much more conductive than the region in the middle. And so the first, you know, part is just draw the kind of cross section like we did in part 1 or question 1 of the other exam, indicate fixed and mobile charge. And so for that, really, it's the same concept where I'm going to have my depletion. I have no bias really, so this is just going to be the 0 bias case. I'm going to have my depletion regions in both the N and the P side, but the N side is much higher doping, right? It's 10 to the 19, P side is 10 to the 16. And so the depletion width will be much smaller in the N side. Hopefully that's tracks with your understanding based off of what we just did for the other exam. And then in the edge regions, so the left and right side, the P doping is actually equal to the N doping, right? And so I'll have equal depletion widths in P and N for those regions. So it's all about the doping, the relative doping This time you don't have to just determine which is P and N, it's given to you. And then just, static negative charge on the P side. And then on both these, and there's also static negative charge here. I'm just going to draw things on the left side, and then you can assume it's the same on the right. And then static positive charge on the N side. Then I have my free electrons here, my free holes here, my free holes here, my free electrons here, or mobile charge carriers. So this is part one. I guess you could say this is the depletion width. Then this here is XP, and that is XN. Any questions about this?
So what about the interface of the P plus and the P? Will that be whole diffusion to the P side?
No, because it's not a p-n junction. So, I mean, you might get some diffusion of holes, but it's going to be the same on both sides. It's not really going to affect anything in this problem. What was the other? Sorry, someone else had a question. Sorry to speak up.
Oh, I had the same question as Yinder.
Yeah, because it's not a p-n junction, there's not going to be any depletion region or anything like that. So you can kind of assume equilibrium. Okay, and so now part B is like really the main part of this problem. Suppose you apply 3 volts to terminals 3 and 4. So this is plus 3 volts. This is plus 3 volts. Yeah, I don't have another drawing. And then this is 0 volts. This is 0 volts. And so this is kind of like almost like a small signal type of resistor where you're given a bias condition, you should find the resistance at this bias condition. Okay. And so you're asked, what is the resistance between terminals 1 and 2? So terminals 1 and 2 there. And so what this ends up being is you have to figure out how much conductive material you have left in the middle of this P region here. And that's going to create your resistor. So what this problem becomes is solving for the depletion widths. And so for B here, the depletion width is going to be equal to 2 times permittivity of silicon. So be careful about this. A lot of people in the homework and stuff, I think, use the permittivity of silicon dioxide for like the MOS depletion capacitors, but keep in mind this is all silicon, right? This is just the formula for the depletion width, 1 over NA plus 1 over ND times the built-in voltage plus my applied voltage, which is V3. It's going to be the same on both sides, though, right? And so the built-in voltage, phi j, is VT ln of NA times ND over NI squared. Give you some numbers here. I usually use 25.9 for this VT, but I think you use 25 in the solution. So if you use 25, you'll get a built-in voltage, I think, of 0.845 volts. And then if you plug that in, right, remember V3, that's 3 volts. NA is 10 to the 16, ND is 10 to the 19. I think at the end of the exam, you're given silicon, relative permittivity of silicon. So remember, permittivity is going to be just 11.7 times epsilon naught. Be careful with units here. Make sure you use everything in centimeters or meters. Don't mix. And if you plug in numbers, you get a depletion width of 0.7 microns. Okay, that's the total depletion width. Now we need to figure out the ratio of the depletion width that's on the P side versus the N side, right? And so really we know that based on that, you can refer back to the charge balance equation I wrote for problem 1 of the 2018 exam. But basically, if NA is smaller than ND, that means the depletion region will be mostly on the P side. So you get this. But another way to look at that is that, you know, the total depletion width is WD. And so I can say that XP, the width on the P side, is really going to be ND over ND plus NA times WD. Right, I can say XN. It's going to be just the opposite. NA over ND plus NA times WD. And you know, that gives me that XN plus XP is equal to WD. So hopefully that you see where that comes from. And then we can actually use this to figure out that XP, because we know ND, NA, and WD now. XP is basically going to be around 1,000 times XN, which, 1,000 times XN, which is basically equal to WD, right? I was saying this earlier, is that most of your depletion region, if you have contrasting concentrations like this, is going to be in one side or the other. It's going to be on the side with lower concentration. And so XP then we'll say is around 0.7 microns. So now if we look at the geometry, or I should say, let's figure out the conductivity. So the conductivity of a piece of material is equal to Q times the mobility times the concentration of free carriers. And technically you have conductivity coming from both electrons and holes, but this actually, in this case, we're in the P material. So this is the conductivity in the P-type material. And so the number of electrons is actually going to be Ni squared over Na, right? When we have a P-type material, we have very few free electrons. And so this number here is going to be much less than Na. And so this is the conductivity really in a P-type material semiconductor is just Q times the mobility of holes times the concentration of acceptors. And so if you plug in, you're given the hole mobility down here is 250 centimeters squared per volt second. You plug these numbers in, you get 0.4 the units are 1 over ohms centimeters. Now, the last thing to do is figure out what the actual resistance is. So the actual resistance of a piece of material is equal to the resistivity rho times the length of that material divided by the cross-sectional area. And so this kind of should make sense if you, this is resistivity. And it's equal to 1 over the conductivity, right? Resistance, conductance are inverse of each other. I'm just going to keep going. Feel free to leave if you like. But this equation should make some intuitive sense to you. Sorry, that's the total resistance, not the shear resistance. Because if I have a piece of material with certain conductivity, or I should say certain resistivity, and I make that material longer, it's going to have more resistance. But then if I make the cross-sectional area bigger, it'll have less resistance. Think of it as like a pipe or something. And so in this case, we found our conductivity. The L is given to be 20 microns. And then the cross-sectional area becomes the width of the material times, yeah, I'm just going to leave this in terms of the variables and you can plug in later. So this is L, and then the cross-sectional area becomes the width times the thickness of that P-type material, which is going to be the original thickness H minus 2 times that depletion region in the P side. So we basically had originally H thickness of P-type material, but then when we put the N-type silicon on either side, we created depletion regions which decreased the effective thickness of conductive material, because that depletion region is like an insulator, right? There's no current that's going to be flowing through that depletion region. So we basically made our cross-sectional area smaller by applying that 3 volts to the N side. And so now we know XP, we know H and WL, we solve for conductivity. We get a resistance of like 31.456 kilo ohms. I went through that quickly, but
Wait, sorry, what is H?
H is given as the thickness
Oh, I see it.
here.
Okay.
Yeah. So basically we're saying that we get that H gets reduced by a factor of XP on either side. Does that make sense?
Do we not have to consider the P plus region?
No, those are going to be really, since they're so highly doped, they're not going to add much resistance at all. I mean, you could calculate the resistance that they add by using the conductivity equation, right? So you would use this conductivity equation down here, and then you would use NA's 10 to the 19. But you would basically get the same, very similar answer if you added those two. It would be 3 resistors in series, right?
Okay.
So you would get a very similar answer.
One thing.
Yeah.
One thing I'm still a little confused about. So it's resistivity between like so V4 and V3, right?
Mhm.
So when we're looking at rho L over A, I assumed L is like the distance between the two nodes, right? So in this case, that would be, I guess, the up and down direction.
No,
if
it's
that
the
makes
resistance
sense.
between terminals 1 and 2 is what we're
Oh,
being
1 and
asked to
2.
do.
Okay, never mind. I understand. Okay, yeah, that makes sense then.
Okay. I'm going to do the first. Yeah.
Just one more question. Is it possible to apply so high voltage between V3 and V4 so that it can form the canal like the MOSFET?
Will you invert it? I don't think so, because you have the same voltage on both sides. Yeah, I don't think you'll cause inversion, because you're not going to have a huge potential across the 2 end sides.
What about the bias between V3 and V2 and like between like the different voltages? Are they gonna affect the movement of the electrons on holes?
So this problem is kind of like I said earlier, it's kind of like a small signal resistance. So we're kind of assuming this bias condition, and then basically to set up the resistance, but we're not talking about any current flowing at this point. No current would really be flowing.
Oh, I see.
Yeah. Okay, I'm going to do the first problem really quickly if anyone wants to stick around and see that. It's very similar. It's similar in a lot of ways to the first problem from the 2018 midterm, in that it's a lot of the solutions are graphical. So yeah. So for A, again, we're told the op amp is ideal. So we're starting out kind of with the simplest case. And we have to find the transfer function. And so I'm not going to work through everything, but for A, really what you do is you should recognize that this looks like a non-inverting amplifier, where this is all kind of, you could group these together, and this is like Z1, and this is Z2, all right, 2 impedances. And so we're basically looking at this amplifier as something that we've seen before. Actually, I'll redraw it. So this is Z1. And this is Z2. So that's our inverting amp. So we know VO over VI will be equal to 1 plus Z2 over Z1. Well, Z2 we know is R2. Z1 is a parallel combination of R1 and C1. So it's going to be R1 over 1 plus SR1 C1. And so if we write this out, we get 1 plus R2 SR1 C1 over R1. You can rearrange this. Again, I'm not going to do it here, but you can check your answer versus this. And you should get that V over Vs is 1 plus R2 over 1. So that's the DC gain. And then the frequency shaping term is 1 plus S times the parallel combination of R1 and R2 C1. And so this transfer function is actually only has a 0, no poles, right? So we have DC gain of 1 plus R2 over R1, and then we have a 0 frequency at 1 over R1 parallel R2 times C1. So you can do that algebra getting that form yourself, but this is what you should get for part A. And then now we're doing a similar exercise where we're now assuming non-idealities. So we're assuming finite gain and bandwidth at the same time. And you're told to draw the Bode plot for this amplifier, so the closed loop amplifier on the graph using the following values. So you're given a value so that you can determine the DC gain and the 0 frequency. And so the DC gain ends up being uh, 11, which is 20.8 decibels. And then the 0 frequency ends up being 175 hertz. Remember, you have to do 1 over 2 pi times 0 frequency because the plot is given in hertz, not radians per second. And so I'm first going to draw the ideal closed loop response, kind of like I did before, where my DC gain is around 20. And then my 0 frequency is, actually I'm going to use dotted lines. You can't really see that. So my 0 frequency is 175. So around there, I think. Yeah. And then I'll go up 20 dB per decade. So this is my ideal closed loop response. Now the open loop op amp response is going to have a DC gain of 1,000 and then a cutoff frequency omega b. Again, this is a property of the op amp of 2 pi times 1,000. So that means that FB is just a kilohertz. And so the open loop response will look like this, where it's 1,000, so that's 60 dB. Oops, change color here. 60 dB, and then it's going to be a single time constant low pass. So at 1,000, it'll start going down by 20 dB per decade. And now, again, I'm going to find the solution graphically by saying my closed loop response, I'll write what this was. This is the finite gain and bandwidth open loop. And then now the non-ideal closed loop response will follow the ideal response until it hits, I guess, let me draw the actual curve, not the asymptotes. So it'll follow the ideal response. Oh, shoot. Until it hits that open loop response, at which point it will start following that and go down like this. So again, I'm really just using my knowledge of Bode plots and my open and closed loop responses to figure out what the actual closed loop response is. I'm not actually solving for any transfer functions, plugging in for the non-ideal open loop response or anything like that. And so, you know, this is 175 hertz and 20.8 dB. This point here is kilohertz and 60 dB. And that's part B. Now, part C says, suppose that in addition to the finite gain and bandwidth, the slew rate is 0.5 volts per microsecond. So this is again similar to that other exam. You're given an input signal with an amplitude and frequency and asked if you would observe output slewing. And so again, we need to consider this frequency. So at 10 kilohertz, we need to figure out what our gain would be. And that's something I can also do graphically. And so at 10 kilohertz, my gain, let's see. So I'll say the magnitude of the gain, VO over VI, so that's closed loop gain, right? At, write it in hertz, at that frequency is going to be equal to 40 dB, which is equal to 100 volts per volt. So I looked at my actual closed loop response to figure out what the gain would be at that frequency. I know it's going to be 100 volts per volt. And so now I can say that VO is going to be equal to 100 volts per volt times my VI amplitude, which is given as 0.1 volts, times sine 2 pi times 10 to the 4th t. Again, I can figure out what the maximum slope of this output waveform would be by taking the amplitude and multiplying it by frequency. And what you should get then for that maximum slope is 0.628 volts per microsecond, which is greater than 0.5 volts per microsecond. This is my slew rate. So I will see slewing. Because my slope of my output exceeds that slew rate. What will that look like? Well, I'll just sketch it here. So if this is my ideal output, what will happen is that at some point that slope will exceed the slew rate and just stay constant at the slew rate until it hits the original, catches up with the original curve, And then as that slope is decreasing, again, it will reach a point where it exceeds the slew rate, and it will just follow the constant. This is, the negative slew rate is that slope, again, until it catches up, and just repeat. So it almost looks sinusoidal because the slew rate is very close to the maximum, right? If I had a lower slew rate, I might have something like this, where I can barely catch up to my sinusoid before it starts slewing again. So I'll just say the slew rate is less than this is like a theoretical slew rate that's less than the given slew rate. But that's generally what this output waveform would look like. The last problem.
Sorry, very quick
Yeah.
on this.
Go ahead.
Can we be, so it asks for to draw it indicating peak to peak voltage values, slopes and time period. So how quantitative can this graph be?
Yeah, so basically in his solutions, for example, like the slope is, I mean, if you said this is a slew rate, I know that you mean it's 0.5, and then basically the slope at that point is like 0.628, because that's where the slope exceeds the slew rate. The amplitude, you can just, you don't have to figure out you don't have to figure out this point if that's what you're asking. Like you don't need to figure
Exactly,
out
that point where they cross, I mean.
No, don't worry about that.
Okay, cool.
Yeah, just, the amplitude here is just going to be 10, negative 10, and positive 10. So I guess if someone's watching this back, don't worry about that. You could, maybe you could write the, so that this signal is going to be at 10 kilohertz. So we'll have a period of 100 microseconds. This is like 50 microseconds. But again, that's for the ideal sinusoid. You don't need to figure out the actual zero crossings or anything like that. It's more of a sketch than a full analysis. Okay, I'll do the last part pretty quickly here. Suppose you replace it with one that's ideal now. So no finite gain bandwidth except for an input bias current of 100 nanoamps into each input terminal. What is the DC output voltage? So I guess the implication that's not 100% clear here is that it's asking for the output voltage for zero input. So this is, a question you might need to, a clarifying question you might have needed to ask. But I have my I bias now. But keep in mind, we have infinite gain, which means that this terminal is virtual ground because we've grounded our input. If that terminal is virtual ground and this is ground here, that means both R1 and C1 have the same potential, 0 volts across them, and so they're canceled out. And at that point, if this is I bias, I know all of that I bias is flowing through R2, right? Because there's no current through R1 and C1. At that point, VO just becomes I bias times R2. So I bias is 100 nanoamps, R2 is 100 kiloohms, you get 10 millivolts of output voltage. Okay, questions?
I have a question about logistics. So, because I've seen a lot of questions on Bode plots, but if we don't have a printer at the time of the test, do you recommend us to print out empty plots beforehand?
That is a good question. I didn't even think about that. Yeah, I mean, so maybe this is for people you're talking about doing it on paper?
Yeah.
Yeah, that might be a good idea to be safe. I have no idea what the exam's actually going to look like, but I guess based on the last two exams having Bode plots, that might be a good idea. Yeah. In the end, though, you can do a sketch of a Bodhi plot too. It's okay if it's not, it doesn't have perfect spacing and things like that.
Okay.
Just remember it's always log. Or
I have a
dB
question
log.
about the body plot.
Sure.
So I'm not quite convinced why when two plot they're gonna reach the graph actually is gonna follow the amplifier, because one is plus 20 dB and the other one is minus 20 dB. My intuition is gonna say, okay, they gonna cancel each other, but
Yeah, so the thing is we're not adding the two responses, right? And so if you were to follow that intuition for, say, a standard low pass type response, I don't know what's going on here, why I can't change pages. What I was going to say is that, for this, then we would see double the magnitude at every point, because you have the closed loop response and the open loop response being the same, and that's not the case. So really, it's almost like I was gonna say you have things combining in parallel, although that's not really true, but you can kind of think of it that way, where you have a dominant response, and that dominant response is going to shape the closed loop response.
so here after 10 to the power 7, we're gonna have minus 40 dB.
Something like that. Yeah, I don't know that the poles will be the pole will be exactly at the same point when you put a finite bandwidth op amp in here, but you will have a second pole that's higher in frequency that will change the slope to minus 40 dB per decade. Yes.
Okay. Okay, thank you.
Yeah, I understand that it's a little hard to just trust that graphical approach.
Yeah,
But
that was
I guess
my question. Yeah.
trust us.
Would be like would a good way to interpret it, like the way I've been interpreting this, like correct me if I'm wrong, is like if you look at like the open loop response, once you hit the open loop response, that's like the maximum that the op amp can give out. So it's almost like you have no other choice but to follow like the open loop response, because you can't get anything more than that, right?
Yeah, I probably should have said it that way. That's a great explanation. Yeah, is that the op amp has this limitation in it, and so if your ideal response is above that limitation, then you'll just kind of stay at that limit.
Oh, I see. Yeah,
Yeah.
that makes sense.
Yeah, thanks, Parth. That's good. Other questions?
One more question about midterm logistics.
Mhm.
How are corrections and clarifications going to be issued?
I guess, we haven't ironed that out, but maybe Piazza is going to be the best way for that.
Okay.
Yeah, I'll confirm with Professor Lin, and maybe we'll do like a post that everyone can add follow-ups on if they have questions, clarifying questions.
Cool, thanks.
But yeah, does that sound like an ideal solution to you? I'm not sure if you guys have had other experiences in other courses. That I'm willing to hear any ideas.
What other courses have done is they usually have like a Google Doc that everyone can be synced up with. That way they don't have to refresh the page and things pop up automatically. And I believe the students either have to email the TAs or go through a form, like a Google form, to ask for clarifications. And then the TAs decide what to clarify on that form so that there's not like a bunch of Piazza hints coming out.
I see. So the students aren't given edit permission for the Google Doc. They're just
right. It's just the
viewing it live.
TAs
Okay.
editing the Google Doc, and the students can view it live. Yes.
I like that. Okay, maybe we'll do something like that. Give you a Google form to submit, and then we will, post publicly any clarifications or corrections. Yeah. Thanks. That's good.
I have a quick question about solutions for this. Will you post the solutions or
No, I don't think
video the
Professor
only
Nguyen's going to post the
resource?
solution. So yeah, this video is basically it as far as, yeah, it's not really on my decision to make, unfortunately.
Okay, thank you.
But yeah, that being said, if there are any clarifications you have or want to have made right now, feel free to ask. I know there was a lot of content covered, but. Okay, I'm going to stop the recording unless there are any other questions.